Question 3. The photoelectric effect may be summarized in terms of the word equation. Photon energy is equal to the work function energy plus the maximum kinetic energy of emitted electrons. Now, just to quickly remember what this means, the energy that's brought in by photons that are incident onto a metal surface will be transferred into the energy required to remove the electrons from the surface. That's the work function energy. And any energy left over, therefore, will become kinetic energy of those electrons that have been liberated from the metal surface. It's also important to remember that the photon energy is HF, always. And the symbol for the work function is phi. And of course, we know that the maximum kinetic energy can be used to calculate the maximum velocity of the electron and even the stopping potential of a photo cell in a photoelectric circuit. Anyway, this question, explain what is meant by a photon. So a photon is a packet or a quantum of energy of electromagnetic nature, or perhaps you'd say electromagnetic radiation. So for 2 marks, that's what you'd have to specify. A packet or a quantum of energy of electromagnetic radiation. Okay, question 3 continued. Why is it that most electrons are emitted with kinetic energy less than the maximum value? Well, the answer for this has to do with the fact that only electrons that are right at the very surface of the metal will gain the maximum amount of kinetic energy, because in a sense they haven't had much energy wasted bringing them to the surface in the first place. Whereas the majority of electrons won't be at the surface exactly, they'll be slightly inside the surface, and therefore some energy will be expended bringing them up to the surface itself. So for 2 marks you have to talk about that. Just to summarize, I suppose, some energy is used for most electrons, bringing them to the surface. And the maximum kinetic energy corresponds to electrons emitted at the surface itself. Okay, part B, same question continued. Light of constant intensity is incident on a metal surface, causing electrons to be emitted. State and explain why the rate of emission of electrons changes as the frequency of the incident light is increased. So here's my answer. Since energy is equal to Planck's constant h times f, we need fewer photons per second for the same intensity. Because it does say up here, light of constant intensity. So to keep that constant, with a higher frequency, we'd have higher energy delivered. But we need less photons per second in order to maintain the same intensity. So that means if there are less photons per second incident, the rate of electron emission decreases, simply because there are less photons giving their energy to electrons per second. Okay, question 4. 3 electron energy levels in atomic hydrogen are represented in this figure, 7.1. The wavelengths of the spectral lines produced by electron transitions between these three energy levels are 486 nanometers, 656 nanometers, and 1880 nanometers. Part 1. On this figure, draw arrows to show the electron transitions between the energy levels that would give rise to these wavelengths. Label each arrow with the wavelength of the emitted photon. Right, so clearly the biggest transition from this level all the way down to this level would have to correspond to the largest energy transition, and that would give rise to the shortest wavelength out of these three, which would be the 486 nanometers. Why is that the case? Well, we should know now by hopefully that energy equals hc over the wavelength. Or if you like, energy of the emitted photon is inversely proportional to its wavelength. So the largest energy transition corresponds to the shortest wavelength given. So this one is the first arrow we'll draw. So labeling that 486 nanometers. Then the second largest energy transition would be from the second level down to there, and of course that corresponds to the 656 nanometer photon, and giving us the smallest one possible. Smallest transition would be those two, from that one to that one, which would correspond to the 1880 nanometer wavelength. So, question 2, following on from that, calculate the maximum change in energy of an electron when making transitions between these levels. So I simply refer to that last equation to calculate this, and plugging in Planck's constant, h, the speed of light constant, small c, and this wavelength 486 times 10 to the negative 9 meters, because that's the shortest wavelength, which corresponds of course to the maximum change of energy. As stated before, we calculate the answer to be 4.09 times 10 to the negative 19 joules. Now, just as an aside, you're often asked to calculate such energies in terms of electron volts, which is another unit, of course, for energy. And just to remind you how to do that is you would take this energy in joules and divide it by the charge of an electron. And so if you did that, you'd calculate 2.56 electron volts.